So you just take sums of every pair of elements of A and of B. This gives you another set. For example, the sum of this triangle and this square is this hexagon here. And these Minkowski sums have always measure bounded from below by some function of the measure of the two sets. And the best function, in a sense, the best function you can take is the measure of A to the 1 over d plus the measure of B to the 1 over d, and the whole thing to the power of c. And this inequality is sharp. So here's an example that shows it's sharp. If you take for A and B scaled versions of the same set, then the sum of them will also be a scaled version of the same set, and the scaling factors add up. And if you're taking volume in RD, then the volume scales with the factor to the power of d. So if you're taking the power 1 over d as in the Minkowski inequality, you get exactly equality. Okay, so this is a nice sharp inequality. It has tons of applications. For example, it gives you a quick proof of the isoperimetric inequality. Okay, but this talk is about discrete versions. So we want to formulate some lower bound of this type for sums of sets, but in the lattice, in Z or in ZD. And if you look at this inequality, you see immediately that it can't be true if you pass to a lattice. Why can't it be true? For example, if A and B are sets that have one element in the lattice, then this inequality gives you a lower bound 2 to the d for their sum in d dimensions, which is false in the lattice, but more generally, this inequality depends on the dimension. If you want anything to hold in the lattice, it has to be dimension free, because the lattices embed into one another. You can put z into z squared. If your estimate somehow becomes stronger with the dimension, this can't work. Okay, so the first step is we want to make this dimension free somehow. And okay, here's an easy, cheap way to build a dimension free inequality. You just do you bound the sum by the geometric mean times 2. And then you take to the power d, you get a dimension-free Brunn-Minkowski inequality. So I have just taken the first line to the power d, and there's a factor 2. How does this work? Okay, this doesn't work. There's a factor 2. I can pull the factor 2 inside the measure because the volume scales with the power d, and I'm taking the d power. Okay, so this is a nice dimension-free inequality, and it continues to hold in the discrete world. I can just replace all the measures by cardinalities of sets. And then if I have subsets of ZD, certainly the measure of the number of elements of the Minkowski sum is bounded below by the geometric mean of the cardinalities of the set. But this is not interesting. This is obvious. Because if A and B are not empty, then the Minkowski sum has at least as many elements as A, and it has at least as many elements as B. So, okay, it has at least as many elements as A times B to the 1/2. So this is the wrong discrete Brunn-Minkowski inequality. It's not interesting. But you can try to make it interesting. We maybe can put something larger than this. And okay, the question that this paper is about is, what's the largest exponent that you can put here? Something larger than 1/2. Okay, so let's see what we can do. We can't do anything. So 1/2 is best possible. You just take the first set that you can come up with. You take arithmetic sequence 0, 1, 2, blah, 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 up to m. Then this has m plus 1 elements. The Minkowski sum with itself has 2m plus 1 elements because it's just the numbers from 0 up to 2m. So on the left-hand side of the inequality, you have something that grows linearly in m, and on the right-hand side also linearly in m. If you would put a larger power, the right-hand side would grow larger than the left-hand side. Okay, but the nice thing is that this example is in a sense the worst possible. So if you prevent this example from happening by assuming that your sets are contained in a small cube, then you can improve the exponent. Okay, so this was proved by Bourgain, at least in this generality. It was first proved by Bourgain, Dilworth, Forth, Kunyagin, and Kutzauer. This is from, they have a paper about explicit constructions of matrices with the restricted isometry property. This is a famous paper, and they prove many things in that paper as, okay, so their goal is to construct matrices that have the restricted isometry property. And to do that, they need a number of auxiliary results, and one of these auxiliary results is this theorem. And that says exactly that you can improve the exponent 1/2 under the assumption that the sets A and B that you're taking the sum of are contained in the cube. So it's that 0, 1 up to m to the power d for a fixed m. Then you can put an exponent larger than 1/2, and the exponent depends on m. Okay. So for their application, all they care about is that you can improve 1/2. They don't care about the value of the exponent. But this talk is about the value of the exponent. So yeah, the question is, what's the optimal exponent that you can put? So this paper of Bourgain and co-authors shows that the best exponent is strictly larger than 1/2. And here's an upper bound. And okay, how do we get an upper bound on the exponent? We just plug in specific sets. And the specific sets that you want to plug in here is just the full cube. So it's basically exactly the example that I showed you at the beginning. You just take numbers from 0 up to m. And if you do the computation, you see that you get the same if you take larger dimensional cubes. Okay, so if A and B are a full cube with m plus 1 points in each direction, then A plus B has 2m plus 1 points in each direction. So you just do the computation. If this inequality holds, then tau m star is bounded by log A plus B divided by log of A times B. And doing the computation, this gives you an upper bound of log 2m plus 1 divided by 2 times log m plus 1. And okay, one remark is this Bourgain and co-authors paper, it obtains an explicit exponent. It's not just some existence result, but they have a specific description of the exponent they get, and asymptotically it's equal to this tau m star. So the ratio converges to 1. The result is already sharp in a sense. It's not exactly sharp, but as you send m to infinity, the ratio tends to 1. Okay, and now the conjecture is that this upper bound is the correct value. So that the best exponent that you can put is the one that you can put for the full cube. Okay.
Excuse me, in what sense is the result asymptotically sharp? Because I mean, this tends to 1/2 finally constantly.
Yes, it tends to 1/2.
So you mean the ratio between this and the result somehow tends to 1 faster than...
Yeah, I guess you have to take the difference to 1/2, something like that. Yeah, you're right.
Even if you subtract 1/2 and you take the ratio, it has to 1, that's what you said.
Yeah, I think that's what I should have said. No, it's a good point. It didn't make sense what I said. Yeah, that's still probably not that interesting. Okay. So what we proved is that this conjecture holds if the cube has 3 elements in each direction. So for m equal to 1, this is, with 2 sets, it's kind of easy to prove. And with more than 2 sets, with more than 2 points in each direction, it becomes a little bit difficult. So we did the first of these difficult cases, and if you take m larger than 2, it becomes, with this method, it becomes very tedious. Probably you can't do it with this method anymore. Okay. Yeah, so this is the first theorem we proved. In that case, the exponent becomes log 5 over log 9. And then we have another result, which is for m equal to 1. So the cube is 0, 1 to the d. Now we can take more than just two sets, any finite number of sets. And this is outside of what I showed you before, but you can make the same conjectures for more than two sets. So first of all, you have the same trivial inequality. The number of points in the Minkowski sum is bounded below by the geometric mean of the numbers of points in the set. By the same argument, it's bounded below by the maximum, so it's bounded below by the geometric mean. So the geometric mean would be a power 1 over n. And then you want to improve the power 1 over n to something as large as possible. And if you plug in the full cube, the exponent you get is again log. Okay, it's some exponent, and it turns out it's log n plus 1 divided by n times log 2. And we prove the inequality with this sharp exponent. And okay, the first theorem is new. The second theorem, it turns out, was not new. This is known since 85 and independently since 88. So people keep proving this without knowing that it was proved before. We also didn't know that this was known. The only person who knows these things is Ben Green. So he told us that. Okay, so those are the two results. And what I want to do now is I want to talk a little bit about the basic idea that goes into this proof. And in the end, it comes down to, okay, there's a nice argument, a nice reduction, how you can reduce this to inequalities in a small finite number of variables. And then there's, okay, you have to verify these inequalities in a small number of variables, which is always annoying. But there's a certain trick for doing this that we used a lot in this paper, and I want to show you the reduction and the trick. And then if there's enough time, probably there is enough time, there will be another different Brunn-Minkowski inequality in the discrete setting in the end. Okay, so how do you prove a Brunn-Minkowski type inequality like this? So it goes via the Prekopa-Leinway inequality, a discrete version of the Prekopa-Leinway inequality. And just to keep this parallel between the continuous and the discrete setting, I wrote down the continuous Prekopa-Leinway inequality. So it's like a functional version of the dimension 3 Brunn-Minkowski inequality that I wrote. If you have two non-negative measurable functions, then you can form their maximal convolution, which is this function in the first line. It's like a convolution, but instead of taking an integral, you take a supremum. So you have a function f, you have a function g. If you want the value of the maximal convolution in a certain point, you take all pairs of points that sum to that one, you take the product of f and g in these points, and then you take a supremum over all choices. Like a convolution, but you take a maximum instead of the integral. And here it's evaluated at x over 2. So the Prekopa-Leinway inequality says that the integral of this maximal convolution to the power 1/2 is below by the integral of f to the 1/2 times the integral of g to the 1/2. Okay, you could ask why. Am I showing you this? It has nicer properties. We will see this in a second, but for example, this Prekopa-Leinway inequality, if you know it on the real line, you can iterate it to obtain it in RD. We will do this later, but for now, the main reason why we care about the Prekopa-Leinway inequality is because it implies the Brunn-Minkowski inequality. If I plug in characteristic functions of sets A and B, then this will be the measure of A, this will be the measure of B to the power 1/2, and on the left-hand side, you get the measure of a plus b over 2, because this maximal convolution of two characteristic functions is the characteristic function of the sum of the sets. Okay, maybe this takes some time to see this, but if these things are both 1, this means that there's a point which is in the set A and a point which is in the set B, such that their sum is equal to the point where you are, which just means that the point where you are is in the Minkowski sum. Okay, so the upshot of the slide is there's a Brunn-Minkowski inequality. It has nicer properties, it's easier to prove than the Brunn-Minkowski inequality, and it implies the Brunn-Minkowski inequality. So we will prove a Brunn-Minkowski inequality in the discrete setting instead. Okay, in the discrete setting it looks like this. So now instead of non-negative functions on Rd, we have non-negative functions on the cube. 0, 1, 2 to the d. And instead of an exponent 1/2, we have our exponent p, which is log 5 divided by log 9. Now, this is like the integral of g to the power 1/2, and now it's the sum of things to the power p. This is the same, right? We just replace the integrals by sums, and the powers 1/2 by powers p. And this here is like the maximal convolution we had before. It's the maximum over all choices of points, j and k, that sum to I of the product of f in the point j and g in the point k. So this is just directly Brunn-Minkowski translated to the discrete setting with powers p everywhere. Okay, and as I already said, so first of all, this implies Brunn-Minkowski in the discrete setting by the same argument as before. And then the crucial property is you can iterate this. You can prove this by induction on the dimension. If you know it in dimension 1, you know it in all dimensions. Okay, and I will show you how this works. So let's assume we know the discrete Brunn-Minkowski inequality in one dimension, when d is equal to 1. And because we're proving it by induction, we can also assume that we know it in dimension d minus 1. And then we want to lower bound the integral of this maximal convolution and to the power p. And I've abbreviated so this brackets 4 as the set of points 0, 1, 2, 3, 4 to make this slide a little bit easier to read. Okay, so by the way, this is the same argument that works on Rd. So this is a general principle. You can iterate Brunn-Minkowski type inequalities. Okay, so you can do Fubini. The sum is the same as summing over the first index, over the first component of I, and then over all other components. Or the other components lie in a d minus 1 dimensional cube. Similarly, you can split up the maximum into maximum over the first component and all the other d minus 1 components. And here I just wrote out f explicitly, it depends on the first and all the other components. Now you can swap sum and the maximum, that makes the expression smaller. And now the point is that this expression inside is the left-hand side of the discrete Brunn-Minkowski inequality in one dimension smaller. So you can apply by induction to one dimension smaller thing. It gives you the right-hand side of the Brunn-Minkowski inequality in one dimension, in d minus 1 dimensions. And now this expression here is the one-dimensional version of Brunn-Minkowski. So you apply that, you get what you want. Okay, so this is the reason why these Brunn-Minkowski inequalities are nice. What's the conclusion of this computation? Conclusion is if you want to prove Brunn-Minkowski, we just have to prove Brunn-Minkowski. If we want to prove Brunn-Minkowski, we just have to prove the one-dimensional Brunn-Minkowski. And the one-dimensional Brunn-Minkowski is just a 6-variable inequality. For all x0, x1, x2, they are just the values of f f of 0, f of 1, f of 2. And all y0, y1, y2, they are the values of g. This maximal convolution is bounded below by the sums when p is equal to log 5 divided by log 9. Okay, this is in principle, you could say, okay, we could verify this by a computer, or something like that. But that's not what we want to do. So how can you further simplify this inequality? Okay, the first step is its scaling invariant. So you can, in both sides, scale with the power p in x and in y. So you just assume that the x is summed to 1 and the y is summed to 1. And then the right-hand side just becomes 1. Looks even simpler. If you want to keep the dimension count, now there are 4 dimensions because we have 6 variables, but we have 2 conditions that we could in principle use to get rid of one of them. Okay, and now you can further simplify this. So we have a sum of maxima of things. And locally this maximum is, the maximizer is constant, so locally this is just equal to xj times yk for certain j and k. And you want to know when are these j and k equal to some given j and k. So you want to write, for example, that this maximum j plus k equal to 2 of xj yk. This is equal to x0, y2, let's say. And this holds if x0, y2 is larger than or equal to x1, y1, and x0, y2 is larger than or equal to x2, y0. 2 conditions. And for each assignment, so there are 4 maxima. For each assignment of these maxima, you get some conditions. If you know that all the conditions hold, then you can just replace the maximum by this. But if you look at these conditions, they are linear conditions in X. So the sets on which your maximum is equal to one of these functions, they are defined by linear equations. And the functions you're looking at are like x, for example, here it's x0 to the p, because that's the power p actually. So this is a concave function, p is less than 1. So we want to minimize always a concave function over a set that is given by some linear inequalities. Now if you minimize a concave function, the minimum is never in the interior of the domain, it's always at the boundary. But if you're defined by linear equations, then you can further move on the boundary until you hit the intersection of 2 linear equations, then you can further move on this intersection until, so you end up in the corner of your domain. Or in other words, you can assume that of these linear conditions, a maximal set of them is satisfied with equality. Okay, so a simple function that we are minimizing is concave, and we are always minimizing it locally over like a polyhedron. We can just move to one of the corners. The minimizer is always in one of the corners. And now you can just look a little bit, like if you have to write it down, you can write down what all the corners are. You have like 3 or 4 cases. And in each of these cases, you get rid of 2 more variables. So you can reduce this to 2 variable inequalities, a list of them, 1 for each corner. And then it remains to verify these 2 variable inequalities. Okay, yes?
And why did you not drop for 4, for example, from 0, 1, 2? If you have a cube with one size bigger.
So this always works, but if you do m larger than 2, then you get a lot more of these corners.
And so it's just so tedious that it's not possible to check even on a computer?
Okay, I have never tried to check this on a computer.
Because if it's dimension 1, it's like a very specific.
Yeah, so in general, you get 2m plus 2 many variables here. So with 4, you would get 8 variables.
But it's just a system of very complete equations that don't have any parameters in them.
Yes.
Basically. Can't a computer do that?
Maybe it can.
Okay, I mean, I'm asking that because I also don't know how to do that on a computer.
So I tried for the next case, when m is equal to 3, I tried to write down all the cases. You know, it was like 20 cases. And then you are not done, right? In each case, you have 2 variable inequalities that you still have to check. And then I mean, maybe a computer can do that. Yeah. But I think, at least if you want to have a proof that works for all m, this is probably not the correct approach, even with a computer. Okay. So, but this was basically all I wanted to say about this. I don't want to show you the 2 variable inequalities. I want to show you one example later. But, okay, it's certain inequalities, they are ugly, you can prove them. I want to show you how, like what is the idea that we use to prove them without computer, just by hand. And so what we always use is Descartes' rule of signs, which is something that is known. Probably most of you know this, but it's extremely useful here. And maybe it's useful in other places as well, I don't know. And this is a slightly more general version than the usual rule of signs. So Descartes' rule of signs is a criterion. It's a rule that allows you to upper bound the number of zeros that a polynomial has on the positive real axis. And it just says the number of zeros on the positive real axis is at most the number of sign changes in the coefficients of the polynomial. And the point here is, this is not just true for polynomials, it's true for arbitrary sums of powers of x. So if you choose any real sequence, alpha 1 less than alpha 2, and so on, up to alpha n, and any sequence of real coefficients, then you can form this polynomial with real powers. And this is still true. The number of zeros of this polynomial is at most the number of sign changes in the CIs. Okay, in case you haven't seen this, or in case you don't believe me that this holds in this more general setting, here's the proof. So we want to do induction on the number of terms. In particular, we can assume that this is true for the derivative of p. So I should get the order right. So first we multiply our polynomial to get rid of the first coefficient and the first x to the alpha, just by dividing by the first coefficient and x to the alpha 1. This doesn't change the number of zeros because we are dividing by something which is not 0. And we are multiplying each coefficient by the same number, so it also doesn't affect sign changes in the coefficients. Then our polynomial starts with 1. So if we take a derivative, it will have 1 term less. And if we do induction, we can assume that the theorem is true for the derivative, just by induction on the number of terms. Okay, and now you can draw a picture. You have your function on the positive real axis. It will look something like this. You want to count the number of zeros. Between any 2 zeros, there must be a 0 of the derivative by Wallis theorem. So the number of zeros of p is at most one more than the number of zeros of the derivative. Okay, and now there are 2 cases. If C2 is less than 0, if I take the derivative, I lose the first term. So I lose 1 sign change in the coefficients. I also lose at most 1 0. So if the statement holds for the derivative, it holds for p. and the other case is C2 is positive. In this case, we don't lose a sign change in the coefficients, but in this case, actually, it looks like this. Because if C2 is positive, then near 0, P is increasing. Because the C2 x to the alpha 2 term is the one that matters near 0. So there will be another maximum before the first 0. So actually P prime has the same number as 0, of zeros at least as P. So in the second case, P and P prime has at least as many zeros as P, and it has the same number of sign changes and coefficients. So again, this rule of signs for P follows from P prime. Okay, and nothing in this proof depends on the exponents being integers. This just works. Okay, but actually I think this kind of depends on this being powers. You can try to write down a more general version with different functions instead of the x to the alphas. And you get some conditions, and I think it basically only works for powers of x. Okay, so how do we use Descartes' rule of signs? So here's an example application. This example application comes from the case m equal to 1. So this is not actually what comes up in our proof. In our proof, a more complicated inequality comes up that you get when you set m equal to 2. But I don't want to show the complicated one. I want to show something that is possible to follow. So we're doing the case m equal to 1. Then you do the same reduction. You reduce to some discrete Prekopa-Leindler. The discrete Prekopa-Leindler follows from the one-dimensional discrete Prekopa-Leindler. And for 2 points, the one-dimensional discrete Prekopa-Leindler looks like this. You have 4 variables, x0, x1, y0, y1. On the left-hand side, you take their maximal convolution to the power q. On the right-hand side, you take their sums to the power q. And q is now log 3 divided by log 4. It's a different exponent because it's a different cube. And if you continue doing the proof that I showed you, you reduce to these corners, then one of the cases that for which you have to verify this is when x is equal to y. And because of scaling, you can assume that they have the form 1z for a certain variable z. If you plug this in, on the right you get 1 plus z to the cube 2 times, so 1 plus z to the 2 cube. And on the left, the only time this maximum is not trivial is when they sum to 1, and in this case it's the maximum of 1 times z and z times 1, which is z. So what you get on the left is 1 plus z to the cube plus z to the 2 cube. Okay, if you don't follow this, it doesn't matter. What matters is we want to verify that this inequality holds for all non-negative z, when q is equal to log 3 divided by log 4. Okay, this always holds when z is equal to 0, then both sides are 1. And the future of this inequality is q is chosen to make the inequality sharp on the full cube. And in this setting, this means q is chosen to make this sharp when z is equal to 1. So if z is equal to 1, this is 2 to the 2 cube, which is 2 to the log 3 divided by log 2, which is 3, and this is also 3. So these inequalities, they are all built to be sharp at 1, and they are automatically sharp at 0. Okay, so this is what we want to prove, and here's a picture. It shows you that this is a sharp inequality. I mean, at 0 you have equality, then the thing is a tiny bit larger. I don't know if you can even see this. Probably it's just one line, and then 1 they are both equal. Okay, and here's a picture of the ratio. So in the best point, the ratio is equal to 1.02. They're basically equal. And you can also see that the program that I used to plot this is not able to compute this accurately enough, right? It starts wiggling around, which it shouldn't do. Okay, so we want to prove an inequality. We know that it holds at the endpoints. Here it's true, here it's true. We have to prove that this function is larger than 1 in the middle. One way to do this is you compute the derivative, you show that the derivative changes sign at most points. Then we can check that it's positive here. That's very easy because it's basically infinity. It is infinity as you approach 0. So we know the derivative is first positive and then it's negative, which implies that there's no minimum inside. So the minimum must be at the boundary, and then you know the inequality. Okay, so our goal is to show that this ratio, the derivative changes sign at most points, which is what we can do with Descartes' rule of signs, except that this is not the ratio, it's not a polynomial. And we can't massage it in any way to make it a polynomial, because it contains a power 2q, which is not an integer. So no matter how many times you take derivatives, it will always be a non-integer power. So what you do is you take first the logarithm, then the strange exponent goes away, then you can take derivatives, and you get polynomials. And yes, so you take a logarithm, then you can still do the same argument because the logarithm is monotone. You still have to show that the derivatives change sign at most ones. Sorry, I was too quick. So before I do this, I show you why I only care about 0, 1. I wanted to show the inequality for all positive z, but it's enough to look at 0, 1, and that's because there's a symmetry. So the polynomial on the left has a symmetric coefficient sequence, 1, 1, 1. So if I flip z to 1 over z, and I multiply through by z to the 2q, I get the same polynomial, and the same is true on the right. So swapping z to 1 over z doesn't change whether this inequality is true or not. And because of this, you only have to look at the interval from 0 to 1. And yeah, we also have equality at 0 and at 1. Okay, and now I have this horrible term. What did I do? So I take my ratio that I showed you, then I take the logarithm, as I said, to get rid of the 2q, then I take the derivative. So this term on the right is what I want to show has at most one sign change between 0 and 1. And then I'm just multiplying by something to clear denominators. It doesn't matter what I multiply by as long as it's positive. And this is clearly positive. Okay, so I'm taking a logarithm, then I take the derivative, and then I clear denominators. And some magic happens. It's a very nice, at least compared to what you could get, it's pretty nice. It just has 4 terms, and I ordered them. So this is a polynomial as in this rule of signs. And you can count, there's 3 sign changes in the coefficients. Okay, so we have proven that this function has at most 3 sign changes, which is bad because we wanted 1 at most. Okay, but it doesn't matter because we have this symmetry. The function is symmetric under z to 1 over z, or at least the set of zeros is symmetric. This is still true for this function. So if there was more than 1 0 between 0 and 1, there would be at least 2. By symmetry, there would be another 2 between 1 and infinity. So in total, there would be at least 4. And actually, there's another 0 at 1, which you can just check. So there's at least 5, which is more than 3. So there can't be more than 1 0 between 0 and 1. Okay, so you have proved this strange, sharp inequality with the rule of sign trick and some symmetry trick. Okay, and then this might seem like it's some isolated trick. Maybe it is, but we use this all the time in the paper. There's 5 or 6 different places where you can use exactly this trick, and it works. So here's a more general statement, which generalizes the inequality I just showed you and which follows from this. And this is also something which you can check on the computer. You see that it's true, but it's extremely hard to show. And okay, a couple of weeks ago I talked to Felipe Gonçalves, he told me that he found this inequality somewhere in some old papers, because people were apparently interested in this. So this seems to be known somewhere already, but it's really not easy to prove. But it follows directly from this method that I just showed you. Basically, okay, it's a similar proof. It's a little bit more complicated. You get not 4 terms, but like 16 or something, but it still works. So the general form of what I showed you is you take a geometric sum, so a polynomial of degree n, which is 1 plus z up to z to the n. And then you want to take 2 such polynomials. They match at 0, because they both are 1 at 0. You want to match their behavior at infinity by taking a certain power. So you take Pn to the 1 over n and Pm to the 1 over m. And at infinity, they both behave like z, because the highest order term in both of them is z to the n. And then you want to further match their values at 1. And this you do by replacing z with z to the s for some s. And then to keep behavior at infinity, you have to take the whole thing to the power 1 over s. And to get the correct value at 1, you have to choose s equal to n times log n plus 1 divided by m plus times log n plus 1. Okay. Doesn't really matter. But the procedure is the important thing. You have the same behavior at infinity, then you substitute some power of z to make it have the same value at 1. So then you get 2 things which agree at 1, 0, and infinity. And the statement is, this operation is monotone. If n is larger than m, then this function defined in terms of n is larger than the one defined in terms of m. So in the special case where n is equal to 2 and m is equal to 1, this gives you the inequality that I showed you before. Okay. So this looks complicated, but I just want to show you the general version of this theorem. Okay, so here I have 1 plus z squared on the left-hand side, and I substitute some power, so it becomes 1 plus z to the q plus z to the 2q, and on the right-hand side I have 1 plus z, so just the case where m is equal to 1. Okay. So this was the proof of these 2 theorems. So I only talked about the proof of the first theorem. The proof of the second theorem is you have to do a little bit more because you have more than 2 sets, but you start with the same reduction. You prove the Prekopa-Leinkler type inequality instead of the Brunn-Minkowski inequality. This one, it's enough to prove it in 1 dimension. And then you use some more tricks, but in the end you again use this Descartes rule of sign trick. Okay, so now I want to show something else, which is a different discrete Brunn-Minkowski inequality. So the previous one became interesting because we made it sharper. In the beginning it was not interesting, but you can increase the exponent, then it becomes interesting. It has applications, for example, to this Bourgain paper. This is something else. This is interesting because it implies the continuous. Okay, so the question is, can we find the discrete Brunn-Minkowski inequality which implies the continuous one? And the answer is you can find one. For example, Matoshi, Rusha, Shaka, and Shezov have found a discrete Brunn-Minkowski type inequality that implies the continuous Brunn-Minkowski inequality. This looks ugly, okay? Looks complicated. But what is important about this inequality is that they can add. Okay, so first of all, A and B are now arbitrary sets in ZD. They are not restricted to a cube anymore. which is okay because we are putting other exponents a and b on the right. So there's no improvement in the exponent, so it still makes sense that this holds on the full lattice. But what's important to recover something continuous is you're also adding another set B, which is contained in 0, 1 to the D. So yeah, here I wrote how this implies the continuous Brunn-Minkowski inequality. You can choose P in the correct way, and you choose V equal to the full cube. Then this inequality implies this inequality, which looks like Brunn-Minkowski. So on the right-hand side, you have the cardinality of A to the 1 over D. In the usual Brunn-Minkowski, you would have the measure of A. The same for B. And on the left, you have the cardinality of A plus B, plus this discrete cube 0, 1 to the D, and then the whole thing to the 1 over. Why does this imply the continuous Brunn-Minkowski? So the idea is you take a set, two sets, and you cut them into small cubes. And these small cubes, they have some lower left corner, which is in some lattice. Then you apply the discrete inequality to these corners. And the sums of the corners are exactly the corners of the sums of the sets, except that because you're having small cubes, if you add two small cubes, you get a cube that has double the size. So you have to add the corners that are like 1 apart in each direction from the corners you already got. So you have to add 0, 1 to the D. So if you want to do the natural discretization of the continuous Brunn-Minkowski, you have to do this inequality. Okay, so this is the better candidate for a discrete Brunn-Minkowski inequality. But you get this kind of dependence on a dimension. You always have to add something which depends on the dimension. Okay, so maybe I should have just showed you this and not showed you the other theorem, which is just confusing. The reason why I showed this is because they proved this inequality in their paper from 2022, and then they asked a question about a possible way of sharpening this inequality. So this is the same inequality, just except for the strange factor on the right. Instead of this factor, they put just b to the 1 over c. Oh, sorry. So here we have some factor depending on p, q, and d times the size of v. And here we just have the size of v to a certain power. This is a stronger inequality than the previous one. That follows from the conditions on all these sets. So you just use how large the set B can be. You use how the exponent is defined. You see that this is a stronger inequality. And this is a natural strengthening of what they did. I guess it's natural because it looks a little bit nicer. But they asked this as a question in their paper, because they were aware that this would be nice to hold, but they weren't able to prove it. And what I'm trying to get at is we can prove this inequality using, again, the same trick. So to prove this inequality using similar reductions as before, so you reduce to some nice function inequality that you can prove by induction on the dimension. Then you reduce to a inequality with finitely many points. And the inequality you have to prove in the end to verify this becomes just this. It's just a one variable inequality. And this one variable inequality you can again verify by taking a logarithm, taking a derivative, and applying Descartes' rule of signs. Okay. And that's the final thing I wanted to say. Thank you.